SAFE Software is pleased to present the 2009 FME International User Conference. This session is presented by Ryan Boyce, who has worked at Burns McDonnell for the past 10 years as an information management specialist. Ryan has a graduate degree in geography from the University of Kansas and is also a Sun-certified Java programmer, a Microsoft-certified application developer, and a Microsoft-certified professional developer for .NET web development.
Well, thank you all for coming. Wes and I are going to talk about a case study that we did for the South Florida Water Management District. We basically, we're trying to animate a lot of their data in Google Earth. So the title of the presentation is Animating Extensive and Dynamic Data in KML and Google Earth. Just want to give you a little background on the South Florida Water Management District. Essentially, they manage an area of 16 counties, and it's a lot of water resources for both users, urban areas, and wetlands, including the Everglades. Essentially, they need near real-time rainfall information to better manage their water resources. And so what they've done through time is they process a lot of radar images, and they've actually created 34,000 of what they call virtual rain gauges. And essentially each one corresponds to a 2-kilometer square pixel, and it records the accumulated rainfall in that pixel every 15 minutes, and they feed this into their system. So their hope is that they can capture all this rainfall information in almost near real time and be able to manage their water resources from it, so they can make accurate decisions on how much water flow they want to release to the urban areas and also back into the water resources like wetlands. They've been doing this for a very long time, so they have quite an extensive data set, and they're also very techno-savvy in the sense that they process all this data in Oracle, and they've been doing it for years, and they have Google Earth Enterprise, and they also have ESRI products built on top of this, so they're very techno-savvy. Just wanted to point out real quick that their existing application for looking at this rainfall data was an ArcIMS site. It's a pretty good site, but one of the things that it doesn't do is it doesn't actually animate the rainfall. So what they're seeing is basically static incarnations of the rainfall that fell at particular day times. So they've always been wanting to be able to see the rainfall animate, kind of like what you would see on the Weather Channel, but also be able to identify the discrete rainfall values to help them make their decisions for the water resources. I just wanted to talk quickly about some of the system requirements that we had for this project. Obviously, they have Google Earth Enterprise, so they want to show the animations in Google Earth. The data the rainfall data comes in about every 15 minutes, and they have this data for both the rain grid, which corresponds to those 2-kilometer pixels that I was telling you about, approximately 34,000 virtual rain gauges, and they also compile that data into their watershed boundaries. On top of processing that data, we also wanted to establish that they receive imagery from NOAA, and they wanted to be able to show that in Google Earth as well. So they wanted to show for both the statewide coverage and also within regions that break up their 16-county study area. They were talking with SAFE, and they thought that FME Server might be the best way to try to process this data into Google Earth, and to show the animations of the water resources. I'm going to let Wes step in and talk about the use cases that we developed.
Yeah, we were first pulled into this project, and these were kind of the 4 use cases we saw. Looks kind of simple. Bring in reflectivity, which is basically map overlays, raster images. Same with the 1-hour precipitation. The reflectivity is just rainfall at the moment, whereas the 1-hour precipitation is over the last hour. And then request incremental rainfall, and that's again 15-minute increments. And then request rainfall accumulation. They wanted it accumulated over time so they could see how the rain was adding up over a certain period. So it looks pretty simple, right? That's kind of what we thought when we started. So here I'm going to go ahead and show the end product. In the upper left-hand corner.
It's actually showing the 4 at the same time.
We got some video problems.
what we're trying to show is four screens of Google Earth animating the data at one time. So, but you're only seeing one. There it was for a second.
Let's go over here.
There it is.
Okay, we won't animate them. But up here in the upper left-hand corner, it's not quite as powerful as we had planned, but we'll go with it. 24-hour rain grid runs at over a 24-hour period, 1-hour increments. So it's an incremental process. The upper right-hand corner, let's see if we can get that one to run. Yeah. So if we click on them individually, we can see this is 30-day rain grid accumulated. So over a 30-day period, you can see the rain grid accumulate. Here we have that same, except with watersheds. So they wanted to grab rain grids or point data, cell data, and then over watersheds. So that same data is now animating with watersheds or polygons. And then here's an example of the, I had to close that second one. There we go. Here's the overlay, the NOAA port reflectivity, which is rainfall at any given point in time. And I can show that first one real quick here. Yeah, so that's the 24-hour incremental. So rain hour increments over 24 hours. So we go to the next one. So that showed 4 of them, and we actually had 27 use cases. They wanted 6-hour time period showing 15-minute increments. They wanted a 24-hour period showing 1-hour increments, 3-day, 3-hour. You can see those 7-day, 30-day, and the number of frames for each. So we had to do that both for accumulated and incremental, and then also rain grid and watershed. So basically 20 use cases were involved there. And then they also wanted to accumulate from 7 a.m. That's kind of their work day, so they wanted to see how, as far as rush hour and things were affected, what rain was happening in those areas. And then we had 5 others, which was the statewide reflectivity and the 1-hour precipitation, which was broken up into 4 regions. Biggest challenges with this project was the short schedule and limited budget. And because of that, we didn't really have a travel budget. They had already attempted to do this by other means, and not using FME Server, not using us, and they had kind of run out of time and run out of money. So they had a very small amount of money. They actually had a lot more use cases they wanted to do. They handed it off to us with about a 3-month window to finish it up, and a very small budget, which, like I said, we couldn't really travel, so we tried to do it all remotely through Citrix. We couldn't really replicate their system locally because of the amount of data that was being transferred. And that became very problematic just because of the large data sets and trying to work through Citrix. And then the real biggest challenge is this had to work when they had the most rain. So it doesn't really do them a whole lot of good if it works well when it's sunny out, only if it works well during a hurricane. So we had to really, really make sure that we tested it, load tested it, and made sure that on those worst days it passed the tests. And then finally, they wanted to try to keep as much of it as they could within the FME Server framework, within translations, and within Google Earth Enterprise. We did do some custom applications, but we tried to limit that as much as possible. I'm going to pass it back over to Ryan.
Okay, just a quick overview of the technologies that we used. They have Google Earth Enterprise Fusion. They wanted this to be an FME server, and at the time of the project, it was 2008. Likewise with Workbench. All their spatial and non-spatial data is in Oracle, and they use ArcSTE to process it spatially. We're building KML datasets essentially, so that was the version of the API at that time. And then for any custom development, they want it to be done in .NET for the 2.0 framework, so Visual Studio 2005. I just want to talk real quick about their source data. Like I said, there's approximately 34,000 of these rain gauges. So every 15 minutes, they got about 34,000 records being inserted into Oracle. They also process that data into their watersheds, which they have approximately 850. And like I said before, the NOAA imagery is coming through in basically 2 feeds being pushed into a file server. One is for the reflectivity, which is the statewide image, and then they also break up their 1-hour precipitation images into 4 regions. In Oracle, I wanted to mention that they built a bunch of views to basically accumulate the 15-minute rainfall data into the various other time increments, like 1 hour, 3 hours, 6 hour, 1 day, etc. Here's a quick overview of the architecture of the system. Essentially, we have the Oracle data here, and we have the NOAA imagery feeding into, obviously, our translations, which are being scheduled by FME Server. This is updating the KMLs on the back end, which are being referenced by Google Earth Enterprise, and that's being served up to the clients, obviously by Google Earth Enterprise client on their desktops. I wanted to mention too, just the two basic workflows for processing both the NOAA data and then the Oracle data, which they refer to as the near real-time data. So the key points in this slide is that essentially the NOAA images are pushed to the file server every 2 to 8 minutes. And so we don't know exactly when these images are coming into the system. And so we really need to check about every minute to see if there's a new image so we can process it into our KML dataset. And it is possible that, that images may not come in for a while, so they might be delayed. So we determined with the client that 20 minutes was a acceptable timeout to basically allow for missing data, because we need to show that in the animations, because we need to basically have a time sequence that's fluid across the time intervals that the user is viewing. So basically, if we don't see a new image for that reflectivity or 1 hour precipitation, then we basically insert a missing frame inside the KML. Moving on to the Oracle data, essentially, this is more consistent data as far as it being input into the system, because every 15 minutes that's going to take place. But it is possible that there could be delays in the system by the rain gauges. So we have to allow for additionally missing frames, and that data can backfill in after the 15-minute time sequence. So we have to continually check for that as well, because again, our KML animation sequences have to be fluid in the time intervals, because one of the user requirements is that they need to know if they're seeing no data, no rainfall essentially, or if there's missing rainfall in the system that hasn't come in the system yet. Down in the lower left corner, basically, we wanted to show that their spatial data, specifically their watersheds, changes through time. So essentially, we allow for that. We basically run nightly processes to update the spatial data that we incorporate into the KML. So in building the KML, these are the key points in getting all this data to animate properly, because you want to keep the file sizes very small, because it's a lot of data. And so with the NOAA imagery, the key thing was to always reference the images, to the file server that they're placed. And so we don't actually try to incorporate all that image data inside the KML. For the Oracle data or the NRD data, we basically, because there's a lot of features essentially in that data set, that we basically establish kind of a chaining KML design, where basically the parent KML, which corresponds to one of the use cases, basically references child KMLs, which is where all the data is stored, and basically we do it in a compressed format, so it's a KMZ format. One other key point is that we had to separate the feature data from the point data, because if they're incorporated in the same KML, it just doesn't animate very well at all. I'm going to let Wes talk about the FME translations.
Yeah, just to reiterate what Ryan was saying, we had to really break this data up into a lot of different pieces in order to animate. There was no way to get an animation of 30 frames of up to 34,000 pixels and 34,000 points to animate. It just wouldn't work. It bogs Google Earth down. So this is a sample translation on the accumulated size. I'm just going to kind of run through it real quick. We have our two data sources. We pre-process all the features nightly into an FFS file, and what that does is we round the coordinates. We put it in lat long WGS84 for Google Earth, and it's all ready to go and as small as it can be. And then here we actually pre-process. We tried to do the accumulation. within FME, and we just couldn't get FME to run as fast as we needed it to accumulate. Because if you think about it, with the accumulation, every 15 minutes or every hour, we had to basically rebuild all the frames from scratch. Whereas at the incremental, we just added the last frame because it was a separate file. And so it was real easy just to add one more frame. We got new data, add one more frame. But with accumulated, after 15 minutes, all bets were off on that data you had, and you had to start from the beginning and animate all the way through. And that created a huge challenge. So we had to pre-process some of the data, and what Ryan did is created a .NET application that would output that data into a CSV file, and then we just bring that CSV file in and tie it to the features. That's what you're seeing here in the beginning, just joining the features to the attributes. And then here, we for all our KML, we try to do an external style file. We feel we have more control over the way the data looks and works if we take it outside of the KML styler and create our own custom style file that's more static. It doesn't try to create that style each time. It just links to a style file, and that way we can kind of, it helps also with changing things, and if somebody wants to edit a color or thing like that, they don't have to go back into the translation. They just open up a KML and change the color. So that's all this middle piece is doing, is identifying ranges and assigning a style based on the range that it's in. And then here we see where we're breaking up the features into the top would be the polygons that we're going to actually animate. We couldn't animate 34,000 polygons, so what we did was we dissolved those by range and created, went from 34,000 usually down to a couple hundred, made it a lot easier to animate. But we still had to keep the points to where they could click on a single point and see the value of that pixel. And so this bottom part is showing the points being processed and created as a separate file. These are actually then broken out into each frame. So each frame actually is made up of two files, a polygon file and a point file, which are completely separate KMZs. For a 30-day accumulation, you're basically creating 60 separate KMZs that are then referenced. And here's where we do the referencing. We're naming folders, tying into parent IDs, creating our network links, and referring back to, and this will make more sense when I show the actual architecture or the way the table of contents looks. But that's what this is doing. We did have to deal with timestamp issues. Animations all have to be done in Greenwich Mean Time. They're working off Eastern Standard, so we had to make that adjustment, and that's what this little custom transformer is. That actually links to a Tickle script that's got a published parameter. So every 6 months on daylight savings, when they have to change it, they just got to go change one published parameter, and then it affects all the translations, and they're good to go. Here we show, I didn't talk about this down in the corner. The way we used, since the data we didn't know when it was streaming, and some of these translations may take 10 to 12 minutes to run, we may get new data as the translation is running, and we had to account for that. And the way we did that is through CSV files. We always had a CSV file that was created after the translation that said, okay, here's our active data set that we're working with. And so as new data would come in, we'd have a little application that would say, okay, what's new that's been added? We'd compare the new to the active and always do that check, because as it may not trigger that translation. If the translation is already running, we get new data, it's not going to re-trigger that translation. It's going to wait till it's done. We had a little check in FME Server that said, don't run the same translation twice at the same time. Wait for it to finish. Well, we may have gotten new data at that time, and we had to have a real way of making sure that we weren't messing up, because we had so many childs and parents and relationships. Had to make sure all that was concurrent. Otherwise, we ended up getting a lot of blank screens saying I don't have data because the parent got updated, but the child KMZ didn't. And that's what this top part is. This bottom part is getting into the data formatting of the date. This top version is strictly to handle the issue of where you have a missing frame at the beginning on accumulated. We didn't really have a way of handling it if there was no rain, because no data was sent over. That's the way their system works. If it was 0, there was no data sent over, so we had to create kind of a variable, and we did a variable setter. So if the first frame came over and we were expecting data and we didn't get it, it signed it a 0, and we created a blank frame for those first few KMZs at the beginning. And then this bottom part just creates the parent KML of the whole accumulated rain grid. And hopefully it'll make more sense here. So here's the parent KML that's created, and that's strictly a network link. That's linked to each of the network links of time frame, and we assign the animation timestamp to the network link folder, and that way it assigned it to the values and the animation as opposed to trying to assign it to each of the features. We did it at the folder level. And then we have values off, and animation would be the polygons on. So when you go to the next level, they can stop at any frame, turn on the values, and then click on any of these pixels. And even though these are actually large aggregated or dissolved polygons, they can still click on any 2-kilometer pixel and find the value. We've got under 5 minutes. I'm going to pass it back over to Ryan to finish up.
Okay, so we basically established how to get our data into KML format. And to reiterate, the reason that we're trying to get all this data into KML format in Google Earth Enterprise is because of the data, the frequency of updates, there's no way that you can actually fuse that in the enterprise system on the back end. You actually have to do this dynamic KML implementation. So we have our data now in the KML. Now we need to basically schedule the translations to process the data as it's being updated in their system. So we're using FME Server 08, and we're trying to stay as much as possible out of the box because they're not very familiar with FME and FME Server, and they didn't want to do too much of a custom development, especially for the schedule and the amount of budget that we had. So with FME Server, basically what we're doing is we're using basically the console to schedule the translations to run, and we're trying to do this basically when the data has been updated. So they had between 3 and 10 FME server engines that they had access to because we were trying to baseline exactly how many engines they really needed. So and initially this was on a development VM server, so with not the best hardware. So even with 10 engines, it was still fairly slow. So but the key thing with all these translations that it had to be scheduled was that we had to set priorities in FME Server for them because some of the data was being updated at a quicker pace than other data, and we had to let that data get in the queue because with FME Server and the engines, basically they can only process one translation at a time. So we don't want too much backup of the translations that need to be showing current data, essentially. So initially, we wanted to have a monitor service, basically, that just kind of monitored for problems in their system and then do notifications. But as we worked through the project, it seemed like we really needed the monitor service to basically be the service that detects when data is being updated. And then what it does, it basically populates these CSV files with the information that has been updated and then schedule the translations to run off those CSV files. So we kind of took away from the translation for it having to read all of this Oracle data just to see if it's got new data. So that really sped things up. So what were the pitfalls and issues that we ran into? Well, obviously, most of the project was done on this development server that was a VM, and it was actually shared, with ArcGIS server and some other technologies. So it wasn't dedicated to this this project. So everything just ran a lot slower. And then, of course, they have so much data, and it's all in Oracle that when the translations try to process the data, especially when they built these dynamic views, the translation just ran too slow, just loading the data into them. So we also ran into the problem of, we couldn't have these unique features in the KML because there were just too many of them, and the animations just slowed way down, way too slow. So we had to basically dissolve the features, so we had less features, but of course that takes a lot of processing time in the translation, and as you can imagine, these translations are kicking off, at very high frequencies. So they can't take too long, and we only have 15 minutes to get all these 27 use cases done and then start the process all over again. And then, of course, data is being updated actually during that 15-minute time, so there's no breaks, essentially. So what we found is that often, we get a queue backup in the database repository behind FME Server of all of these translations that were just waiting to run. And this usually happened after midnight when all the use cases would kick off, because that's when the 1 day and the 3 day and the 24-hour would be implemented in addition to the 1 hour and the 15-minute. So like Wes had said, we ran into the issue where the parent KML that referenced all of the child KML data sets sometimes would get out of sync, based off of what was being processed. And so what the user would see in the client is they would see, basically errors come up to say that data is not found. You can't find it, essentially. So again, animating was the key, because that's all they really care about, is to be able to see this data in a fluid time sequence. So we really needed to get the performance there, and we were able to achieve that, through the design of the KML, but it took a lot of iterations to figure that out, and we spent a lot of time in doing that. So daylight savings, that's just a minor point. Basically, we had to allow for it, so it just adds a little minor headache when you're trying to process all the time spans in the KML. Walking away from the project, our lessons learned is that, with this because they had so much data and their system was pretty complex, there's no way that we could replicate that into our own site, essentially. So we had to basically say that next time, if we're going to do a project like this, we should basically work on site, because working through Citrix or VPN is just too slow, and oftentimes you couldn't even see the animations in Google Earth because of that. We initially created a translation per use case, but in hindsight, it's probably better to actually have one translation per data case, and that way we limit the number of translations that have to be created, because that just creates a lot of overhead, and there's a lot of duplication of effort in the transformers. Then, of course, how best do you detect data updates in the system, because that's really the key. And so, we brought in the monitor service to do that, but it still has some fallacies. So, always looking for better ways to determine when the data is updated. So we actually we had to create in Oracle basically some temp tables to basically process the data into, because using their views was just way too slow.